Okay, so today we're going to look at some differentiation examples. So say you had y equals ax to the n. If you want to differentiate that, what you do is you multiply everything by the power that you're raising it to. So you get n times a times x, and then you take 1 off the power. So nax to the n minus 1. And that's the general case. And that's going to help us when we look at some more specific examples. But all dy by dx means is that, say you had an infinitesimally small change in x, like an unbelievably small change in x, how much would the y value change? Like, for example, let's say you had y equals x squared. If you did dy by dx, you get, multiply it by the power, so you get 2, and then you take 1 off the power. 2 minus 1 is 1, so that's just x. We won't write x to the 1, we're just going to leave it as 2x. All that means is that, let's say we had the graph of y equals x squared. So let's say we chose a value of x as 2. So dy by dx equals 2x, which in this case equals 4. So what does that mean? It means that if we had a really, really small change in x, the change in y would be 4 times that much. So let's say we increased by x by 0.0000, and then a gazillion million noughts 1. It means the change in y would be 4 times that. Not quite, because it would have to be a lot smaller than that. Like x would have to be, the change in x at least would have to be infinitely small. We say infinitesimally small. But that's the general idea, is if you had an infinitesimally small change in x, the change in y is going to be 4 times that value. So it's also going to be really small, but it's going to be 4 times that. And that just means, kind of in layman's terms, that the gradient is 4. So this guy, the tangent here, the gradient is 4. Okay, so for our first example, we're being asked to differentiate y equals 6x squared over x to the 4. So I'm going to try and make this as simple as possible. Whenever we have random numbers, what I like to do is I like to just ignore them for the time being. So we're going to leave the 6 out here, and then we're going to ask ourselves what happens when we do x squared over x to the 4. So as you know, we're going to cancel the x squared with the x to the 4, and we're going to have an x squared left over. So it's just 6 times 1 over x squared. And that is just, if you remember from index laws, whatever it is, when we have an x on the bottom, we're just going to have the negative of whatever it's being raised to. So it's 6 times x to the minus 2. And then going ahead, we can just go on with what we just looked at. In this case, our a is 6 and our n is minus 2. So we multiply everything by the power, so minus 2. So minus 2 times 6 is minus 12. And then we take 1 from the power, so minus 2 minus 1 is minus 3. So it's minus 12 x to the minus 3. And you might be asked to leave it in a nicer form, so you can write it as minus 12 over x cubed. Okay, so for our next example, we're given y equals 2x cubed minus 3x squared minus 12x. So that's the function, and what we're going to be asked to do is find out when the value of this function is increasing. So what that means is it's a cubic graph, so it's going to look something like this. It's going to start low and then kind of do like this and then go up. We're trying to find when it's going up, basically. So it's going to be like when it's really negative and really positive, but where, basically. So that's what we're being asked to find. So a good place to start, obviously, is to differentiate this. So dy by dx equals 3 times 2 is 6. Take 1 from the power, so 6x squared. 3 times 2 is 6 again, so we got 6. Take 1 from the power, we just got x. And we can think of this as a little to the power of 1 here. So minus 12 times 1 is still minus 12. And then we take 1 from the power, we'll get x to the power of 0, which is just 1. So we leave it as minus 12. So that's our function of dy by dx. So that's telling us what's happening to the gradient, basically. And we're trying to find when this is positive. So when it's greater than 0. So this looks familiar. We've got a quadratic inequality, and we know how to solve these. We looked at them in another video. So we really are just going to do this again. That's one reason that quadratic inequalities are important. for stuff like this. So we're going to want to divide everything by 6 because that's just going to make things a lot easier, because we've got some 6s, we've got some 12s. So we're going to divide everything by 6, and since we've got a 0 on this side, we can do that. So x squared minus x minus 2 greater than 0 minus 6 is still 0. So we're going to want to find our critical values here. So this looks like it can be factorized. So we've got a minus 2 here, and we've got minus 1 as the coefficient of the x. So we're going to want a 2 and a 1. And since we've got a negative x, we're going to want the 2 to be the negative guy. So we've got x minus 2, x plus 1 greater than 0. And just checking, we get x squared minus 2x plus x. That gives us minus x. And then minus 2 times 1 is minus 2. So that's right. So our critical values, our CVs, are 2 and minus 1. So if we want to sketch the graph of this to help us visualize what's going on, we're going to have it cutting the 0, the x-axis at minus 1 and 2. So it's going to look something like this, and then up. And we're looking for when this is greater than 0. So it's going to be the tails here. So we know that the function is going to be increasing when x is less than minus 1 and x is greater than 2. So what that means is our original function, 2x cubed minus 3x squared minus 12x, this kind of the graph of this is going up when x is less than minus 1 or x is greater than 2. Okay, so for our final example, we're going to look at the value of a car, which is given by V after t years of it having been bought. And that's given by 20,000 over t plus 1 plus 1,000. So what we're going to do, we're going to want to work out dv by dt. So we're going to rewrite this as 20,000 times t plus 1 to the minus 1, and then plus 1,000. So we can use the chain rule here to calculate dv by dt. We'll probably do the chain rule in another video. But for now, you just have to take my word for it. What you can do is, it's going to work the same way. We multiply by the power, so minus 1 times 20,000 is minus 20,000. And then we just take the power down by 1. So minus 1 is minus 2. And since 1,000 is a constant, it's going to disappear. It's going to be 0. So what this means is that the value of this car is decreasing every year. That's what the negative sign means. Okay, so all this means is if we did the graph of V against t down here, let's have a straight line. So when t is 0, we're going to have 20,000 divided by 0 plus 1 is 1, so 20,000 plus 1,000. So when t is 0 here, our value of the car is going to be 21,000. So 21,000. And it's going to have a general, it's going to have like the 1 over x shape. It's going to kind of do this. That's the kind of the shape it's going to do. And we can see here that the gradient is negative because it's going down. So that's encouraging because we've got for our dv by dt, we have a negative at the front. And t plus 1 to the minus 2 is always going to be positive because this just means 1 over t plus 1 squared. So since t is always going to be greater than 0, this is always going to be positive. So our value of dv by dt is going to be negative. And so all this means in terms of the model that we have is that the car's value is decreasing every year. And the 1,000 means that after 19,999 years, the value, this will get to 20,000 over 20,000, so it'll be 1. So the value of the car will be 1,001 after 19,999 years. And as t keeps going up, 1,000 is going to be the baseline. So after infinity years, the value of the car is going to be 1,000. Okay, so for our final example, we're going to test our understanding a little bit more. We're going to stretch ourselves. We're given a circle of radius r, and we're being asked to find dA by dr. So that's a little bit weird because we're used to y's and x's here. But when we talk about differentiation, it's not just y's and x's, it's about any two variables. All differentiation is telling us how one variable changes with respect to another. So in this case, it's how the area of the circle is changing with respect to r, the radius. So if we had y equals x squared, if we did dy by dx, all we're doing is we're asking ourselves, how does y change with respect to x? Like if we changed x a really, really small amount, how would the y value change? So we get 2x. And as we've explained, this just means that whatever value of x we have, we multiply it by 2, and that will tell us how our y is changing. But this can be anything. Our y's and x's can be anything. Like if we said z equals x cubed, we would do dz by dx, and that will tell us how z changes with respect to x. So in this case, it would be 3x squared. Sorry, I'm being really unneat here. Just to demonstrate this principle of whatever's on top is what we're trying to find, is what we're investigating with respect to what's on the bottom. So going back to our original example, we need a formula for a with respect to r, just like we need a formula for y with respect to x, like y equals x squared. We know that the area of a circle A is given by pi r squared. And so thinking of A as y and r as x, we're going to do dA by dr. We've got a 2 here as the power, so we're going to multiply everything by 2. Pi is just a constant, so we can leave it as 2 pi. And then we take 1 from the power of r, we get 2 pi r. And that's really interesting, actually. If you notice, this is how you calculate the perimeter of a circle. Perimeter? Is that right? Perimeter? 2 pi r. Circumference. Sorry, the circumference of a circle. It's the same thing, though. And that really baffled me as a kid. Not as a kid. As a GCSE student or A-level student. But if you think about it, it does make sense. Well, if you think really hard about it, I basically, in a rough sense, if you had a circle of radius r and you increase that radius just a little bit, how the area is changing is what you're doing is you're just basically adding another circle to the area. So the area is going to increase by the circle that you're adding, and that circle is going to be given by 2 pi r. So it's difficult to get your head around some of this stuff sometimes when we're talking about infinitesimally small stuff. But that's why, and I think it's really nice, to be honest, but that's just me.